In this lesson, we're going to look at an introduction to probability. Let's start with a simple example. Suppose you throw two distinguishable dice. Remember when I said distinguishable in a previous lesson, I mean that you can tell the dice apart. Suppose they're different color dice or something like that. And look at the sum of the faces showing. What is the probability that the sum is at least 10? Let's talk about the use of the word distinguishable in this problem. The sum has to be at least 10. Let's write our dice as an ordered pair. What's two numbers on the dice blocks that could be adding up to 10? Remember, they only go 1 through 6, so let's say 4 and 6. That's a good example of two choices, but here's where the distinguishable comes in. Let's say we're talking about a red die and a green die. A red 4 and a green 6 could also be a red 6 and a green 4. That's another outcome for this sum of 10. Another one is 5 and 5, and that is the sum being 10. But notice that the problem doesn't just say 10, it says at least 10. So now for 11, you could do 5 and 6. But remember, with the distinguishable, the order matters, so 6 and 5 is another option. And then at least 10 could also be 12, where we're looking at 6 and 6. This is all the possibilities. Now, we'll give a little bit more detail as to why this works, but what I'll tell you here is that you've got 6 possibilities that are at least 10, and you've got 36 possibilities total. Where does that 36 come from? 6 times 6. We actually talked about it in a previous video, and I mentioned to make sure to pay attention to that particular number. We get 1/6 for the probability. Now we need to talk a little bit more about what probability is, but right now just assume that for every 6 throws of 2 dice, one of them will have a sum of at least 10. Now let's look at some terminology. An experiment would be some sort of action, some sort of task, something that we're just working on, something we're doing. And then all the possible results of the experiment are what we call outcomes. All the possible outcomes together make what we call the sample space of the experiment. So the sample space creates everything that could possibly happen, and then an event is some special subcollection of the sample space that fits some sort of criteria. In the example that we just did, the experiment was rolling 2 dice and looking at their sum. The results of the experiment were all the different possible dice rolls, and we could write all of those dice rolls as our sample space. The event was that the sum of the 2 dice was at least 10. And now the probability of an event, which we have this notation, probability of E, is some value between 0 and 1, 0 being impossible, 1 being will happen. You can think of these as percentages as well. This is a number that represents the likelihood of how often that particular event will occur when the experiment is performed. There's 2 different ways to do probabilities. You can either do an experiment enough times, and a lot of times is honestly necessary, but a lot of times what we'll do is assume some theoretical constraints and we'll calculate the probability manually. This particular method is the best way to usually come up with a probability. So here's our main assumption, the idea of equally likely. Sometimes you'll hear this said as a fair die, a die with all 6 sides equally likely to be landed on. A fair coin, heads or tails is just as likely to show up. So if you take all the outcomes and the probability of all the outcomes are the same, then we say it's equally likely. Now if we have equally likely, then we have this formula. The probability of the event is the number of possibilities for the E over the size of the sample space. Let me give you a little notation we often use for that. N of E over N of S. The N simply meaning the number of. So the number of things in the event over the number of things in the sample. Let's consider an example of throwing a die and then flipping a coin. The sample space for this experiment would be all possibilities of throwing a die and flipping a coin. Using some of our basic multiplication, we can say, well, the die has 6 sides. The coin has 2 sides. 6 times 2 is 12. That's what we expect for our sample space. I'm going to use a little notation that you don't necessarily need to know what it means. It's just a curly bracket. you could get a 1 on the die and heads on the coin, or 1 on the die and tails on the coin, or you could get 2 on the die with heads on the coin, 2 on the die with tails on the coin, and so on. You'll notice there are 12 outcomes in this sample space, and this captures all of them. Now consider the event of rolling at least 5 and getting a head on the coin. What's the probability of this event? Let's give E a label. Remember, E is a subcollection of the sample space. At least a 5 with a head on the coin. Well, that means we could get a 5 with a head or a 6 with the head, and that's it. So then the probability of the event, remember my formula is the number of items in the event over the number of items in the sample. There are 2 items in the event and 12 items in the sample, so we get 1 out of 6 for this probability of getting at least a 5 and getting a head on the coin. Here's another way to do probability. This is what we call the relative frequency, sometimes known as the empirical probability. What we do is we run the experiment many times as we feel is necessary to get a good number. Sometimes this needs to be in the thousands to really get a good feel. Then we'll calculate this relative frequency by looking at the number of times the event occurs divided by the number of times the experiment was performed. Now what's interesting is in practice, if theoretical probability is correct and the relative frequency is done enough times, they will actually converge to be the same value. But enough times is just do it and 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 do it, and you'll see it gets closer and closer to the theoretical probability. We call this the law of large numbers. For an example, suppose that a coin is flipped 1,000 times and heads comes up 482 times. What's the relative frequency? The event is getting heads, and there's 482 times that we got heads. We perform the experiment 1,000 times. So we get 0.482 for the relative frequency. If we were to say for a regular coin, we would say 1 out of 2 would be our probability, which is 0.5. However, it's not quite there, but it is close. The idea is the more we flip the coin, the closer and closer it will get to that 0.5 over time. Next example. Suppose we flip 2 fair coins and we want to know the probability of getting exactly 1 head. Let's write out our sample space first. If we flip 2 coins, remember when I told you for probability you must assume things are distinguishable. That is, there's a first coin and a second coin. If you like, think about it as a quarter and a nickel, or something like that. You could have heads on both coins. You could have heads on the quarter and tails on the nickel, or tails on the quarter and heads on the nickel, or tails on both. The event is going to be having exactly 1 head. That's the head-tail or the tail-head category. So if we calculate the probability now, remember that's the number of items in the event, which is 2, divided by the number of items in the sample, which is 4. We get 1/2. So the probability of getting exactly 1 head is actually 1/2. Half the time you flip those 2 coins, you will have 1 head. But now let's look at a possibility that's a little bit different. Consider the following sample space. If this were the sample space, we'd have a little bit of a problem with this probability. Because you would have the 1 head as one of the 3 cases, and you would get a probability of 1/3. That's different from 1/2. So what is the problem? The problem is that if you do this experiment enough times, you'll discover that this sample space doesn't work because the outcomes are not equally likely. These outcomes are not equally likely, so we cannot get a probability from this sample space. Now let's do some basic probability from a marble example. A jar of marbles contains 3 blue marbles, 7 red marbles, and 4 green marbles. If you randomly draw a marble, what is the probability of drawing? And then we're looking at each of the 3 colors. Now I will tell you one thing. There is some sort of weighting going on. The 7 red marbles will definitely be more likely than the 3 blue marbles. It's weighted higher, if you will. And actually we're using the concept of distinguishable right here. We're giving 7 entries for the red marbles. but only 3 entries for the blue marbles. Assuming they're distinguishable is exactly what we need. So now the question is, what is the sample size? If we look at this n of s, we can find it by just simply figuring out how many marbles are in the jar altogether, just by adding them up. I get 14 marbles in the jar. That is going to be the denominator for each of our probabilities. So for a blue marble, well, there's 3 blue marbles out of 14 marbles. There's your probability. Red marble, 7 out of 14, which we can reduce that to 1/2. And a green marble would be 4 out of 14, which we can reduce to 2/7. Last example. This is a little piece of what we call game theory, trying to find a winning strategy of some kind. Consider you and an opponent are playing a game with 2 spinners that you see below. You will win every time you both spin your spinner, and yours has a higher number than your opponent's spinner. Should you choose spinner A or spinner B, and why? You might look at these and say, spinner B has the highest number. If I roll that 8, I win every time. But spinner B also has the lowest number. If I roll that 1, I lose every time. Spinner A has a more well-rounded number system, so maybe spinner A is better. But which is it? The way to do this is look at all the possible outcomes. If you think about it, there are 9 outcomes to this game. 3 choices for the first spinner, 3 choices for the second spinner, and as we've discussed, you should multiply these numbers. Let's write down all of the outcomes. Here's all 9 possible outcomes, where the first entry is the outcome from spinner A, and the second entry is the outcome from spinner B. Let's look at the ones where spinner A wins. In the 4-1 case it wins. In the 4-6 case it loses, and any further it also does. In the 5-1 case it wins, but in the 5-6 and 5-8 it loses. In the 7-1 case it wins, in the 7-6 case it wins, but in the 7-8 case it loses. So these are the winning numbers for spinner A. With that said, spinner B, you'll notice, has the rest of them as its wins, and spinner B has more. Choose spinner B because it will win 5/9 of the time, whereas spinner A will win only 4/9 of the time.